Swayam Prabha. Digital India. Educated India.
Welcome to the class and good day to all of you. Today we will look at the geotechnical reuse of waste materials. In fact, this lecture as well as the next lecture, 2 lectures will be on this topic. So, just if we recall, where is all the waste coming from? We pick up the raw materials from Mother Earth, we put in some energy, do some processing and get some products, and after the products, the useful part of the products have been used, the end waste is the material which is not of use to anybody is waste. So, if I had a magical methodology that all the waste I could break it down into its individual components which were mixed. Let me say that if I have an old car, right, I have used it and now it is not of use to anybody, I can take out certain parts and recycle them. But the painted door, I have a problem. Why? The paint is on the door and I cannot take off the paint. So, if I had a methodology where I could actually break down all my waste into its original components of the raw material from which it was made, then I would have a wonderful solution. I would take any component, take it to that processing plant, and all the raw materials which were in the component would come back again, and those raw materials would again go into the manufacturing process, and therefore I would have a very healthy sustainable society. So, as long as we cannot get back the original raw materials from the mixed products, because they are so intimately mixed, chemically, thermally, electrically, whatever have you, therefore I will end up with this waste. Now, if I have to use waste which is not of any use in any other process, which is the application in which there is maximum potential for consuming it? And if you look at again look at Mother Earth from a far away distance from the top, your trees are growing, your plants are growing, your animals are multiplying, your human beings are multiplying. But one of the non-biotic elements which are growing are cities. So, I have these huge concrete buildings, skyscrapers, buildings, so they are all rising above the ground. And obviously, since they are rising above the ground, the raw materials have come from some place and they are making this rise. Similarly, all the embankments and earthworks are causing materials to be at a higher elevation than what they originally were. So, consequently, one of the potential areas of application is, can I use all my waste materials in infrastructure development? Because in infrastructure development I am using millions of tons of materials. So, how wonderful it would be that I am producing millions of tons of waste which could be used in infrastructure development of millions of tons. Now, it is quite clear that you can't use biodegradable material necessarily for making these buildings which are rising high up above the ground. But is there a component of the waste which is non-biodegradable which can be used? So, one of the segments of reuse in infrastructure sector is in the building material segment, cement, concrete, bricks and blocks. We are not touching that. The other segment is using the waste in geotechnical applications, earthworks, filling low-lying areas, making embankments, whether lakes or roads, backfill behind retaining structures. All these flyovers that you see, they've got retaining walls. Can I use my waste as backfill material? So there also we are using millions of tons of earth every year. So that is what we will look at today. How can we use waste materials in geotechnical applications? So let's just quickly recall the hierarchy of integrated solid waste management was minimize the waste, recycle it, process it, transform it, and then only send a little bit for landfilling. So recycling is again sending back the material, recovering the material to become a raw material for some other industry or for reuse. In waste processing and waste transformation, as I said, if I could magically convert my waste into the raw materials from which the waste was produced, I would be able to consume all the waste. But really, we are not able to do that. We are able to do some secondary processes by which I can recover energy or material from a waste, or we may be able to transform the waste. Transforming a waste into a brick is, I have a powdery material which I could make a brick out. So that's a waste transformation process. Again, to recall, high biodegradable fraction, as in the case of municipal solid waste, we need to do biological treatment and do decomposition, get compost out of it. High combustible fraction, if your waste has got cloth, it has got plastics, it has got wood, it has got combustible materials, do thermal treatment, take out energy by burning it. If you have high inert content like construction and demolition waste, all the silt which you are picking up from the drains, all the sediments which you are picking up from the bottom of canals, which may sometimes be contaminated. But anyways, if you have high inert content, you go towards the direction of physical treatment. That means you will use it either by fractionating them, or you will be putting them in some inert matrix. So separately stored wastes can be used for material and energy recovery, but if you mix everything, if all these are very intimately mixed, then to break it up into its individual fractions is very expensive, and currently it does not work. So when can we and how can we reuse the material for geotechnical applications? As I said, in the infrastructure and the construction sector, reuse can be for building materials, it can be in roads, because several kilometers of roads are being constructed, or it can be that you are using some of the material as a soil. So when you construct a road, there is of course the pavement section at the top, but do remember that beneath the road there may be a long embankment which may be a few meters high and run for several kilometers. So there is a huge potential if waste can be used as soil. So geotechnical reuse is the use of waste material in earthworks to replace soil. Soil becomes the original material, the raw material which you are using for making embankments. So if you can reduce the amount of soil, because you have to dig up soil from somewhere, from some borrow area, and bring it to your point of application, you are either making a hole in the ground, or you are taking a small rise in the ground and excavating it. So you would like to replace the soil, or you can use the waste as an additional layer. But what do we want to replace? Well, when we deal with soils, we deal with gravel, sand, silt, clay, mixed soil, and boulders. So boulders and gravel may sometimes be used as riprap. Can we replace it? Sand is used as drainage material. It can be used as sand drains, chimney drains, blanket drains. Can we replace that with waste? Silt and clay are like normal topsoil or earth on which plants and vegetation grow. So can we use waste for this purpose? So this is what we would like to replace with waste. But where would you like to replace it? What elements? As I said, embankments for roads, embankments for lakes, embankments for reservoirs, filling low-lying areas. Many areas are flood prone. You may be buying a plot for your house and you might find that it's lying at a level below the road level. You are worried that when the rain comes, all the water from the road will come into your plot, so you will raise the level of your ground above the road level to make your house. So filling low-lying areas, we might want to earth fill behind retaining structures, we might want to replace in drains, we might want to replace in clay barriers, in covers, etc. If you can get geotechnical reuse, then the advantage is that it is used in large quantities. You may, in one project, use millions of tons of the waste. So when I consider a material for replacement of soil, what is it that I should be 100% sure about? I'm tempted but I should be sure that it is not classified as hazardous material. If it is hazardous, don't touch it. I should be sure that it does not have significant biodegradable content. You see, all design life of any civil engineering structure is 50 to 100 years. So, if I have high biodegradable content, the material will go volume reduction with time, because the organic matter will eventually, or biodegradable matter will eventually decompose. So, typically for soils, a 3% limit is what we have been traditionally dealing with. Less than 3% organic material is fine. This can be extended to 5%. But if you have got 10-15% of biodegradable material, be prepared that it will settle with time, and it is not due to consolidation, it will be secondary or creep kind of behavior. I should be clear that the particles will remain physically and chemically stable in the long run. And basically you should have a silica matrix. Can you have a calcium carbonate lime matrix, limestone matrix? Well, limestone has solubility in acidified medium. CaCO3 plus 2HCl gives you CaCl2 plus CO2. So, whereas SiO2 plus 2HCl does not do that. So, there is an issue. If you have limestone, if it is in a protected environment, it will work, but on a long term basis where there are going to be spills of acids, or there may be an acidified environment, you may have an issue. So, even in natural limestone formations, geologically you find some seepage channels or channels which have dissolved over a geological time frame. So, particles should remain physically and chemically stable, should not contain deleterious material. It may not be classified as hazardous. As I said, suppose your waste has got common salt in it. There is no standard that soil should have less than 1% NaCl or 2%. It may not get classified. Under the TCLP procedure, you may not have any problem. But if any sulfate or any chlorides or any total dissolved salts are coming out of the material, that's not very good, because it can harm other things. So, it should not contain deleterious material. Particle size should be such that standard earth moving equipment can be used. I don't want a waste which is having 1 meter by 1 meter by 1 meter blocks. Neither my dozer nor my compactor will work on it. Then I have to first crush it, bring it into a soil size range where our earth moving equipment can move. Typically, earth moving equipment works well with gravel, sand, silt and clay. So, we need that particle size range. And it should not harm groundwater quality. Whatever are the constituents, you must be 100% sure that if once you are putting soil on ground, it should not harm the quality. And it should be fairly homogeneous. You design an embankment with the waste, it's coming in. Today it's coming in as in the silt to clay range, tomorrow it's coming in the silt to sand range. That means as you are building the embankment, the soil is changing. You do want fair homogeneity, that means lack of heterogeneity in your material. It may gradually change, it's fine, but if you are digging up from some place and suddenly you are finding material is changing drastically, and in the same length of the embankment, at one place it's a fine grained soil, and the other place it's a coarse grained soil, you can design for it, but then you have to have your embankment section changes. You're making a lake embankment, the fine grained soil was fine, suddenly you find a lot of coarse grained content, seepage may start to be excessive through that part. So, then you have to make those design measures. So, it should be fairly homogeneous and have low variability. If you can do all this, you've got a good material. So, let us see what are the materials which are traditionally used. If you go to the developed countries, what is being used? Reclaimed paving materials. So, in the developed world, typically you do not put overlays on your pavements. You dig up your pavement. In India, you put overlays. Your road has gone bad, what will happen? Next day somebody will put another layer of the pavement material. In the developed world, you dig up, remix more bitumen and asphalt and relay the road. So, reclaimed paving materials, if there are some rejects from that can be used as soil. Coal ash, fly ash and pond ash is used. Rubber tires are used. Rubber tires are difficult to dispose. Blast furnace slag. Slag is a term. What does the word slag mean to you? Chemistry, 10th class, 12th class. What is slag? Slag is an impurity. So you are wanting to take out steel, you want to take out iron, so you will have iron ore. The ore will have how much iron? 90% iron and 1%? No, it's the other way around. So ore, which we call rich ore, may not have more than a few percentage of the main material. So you will crush it and grind it and you will get tailings. But beyond that, you will want to further refine the material, then you will go into a chemical process, a froth flotation process, a gravimetric process, air separation, or whatever. Eventually, you will get something called impurities. Those impurities are slag. And what will the impurities mainly comprise of? The original rock. However, in the processing, you may have added a lot of things. So beware, all slags may not be good material. But if a slag doesn't have hazardous component, you can use it. If a slag doesn't have hazardous component, you can use it. So you can have blast furnace slag, steel slag, all kinds of slags. Coal bottom ash can be used separately, mine tailings can be used. So this is what is being used in developed world. In India, what are we using? We are using fly ash. When I use the term fly ash here, it basically means pond ash, because fly ash is not available individually that much, and whatever an individual fly ash is available, it is going to the cement plants because of its pozzolanic activity. So what is available to us is ash which is lying in the ponds, which the cement plants don't want, because the fines have actually got washed away. So we can use pond ash, we can use mine tailings if they are not classified as hazardous. Important. We can use construction and demolition debris, but we have to process it, we have to crush it and bring it to workable size. And initial studies are underway. Can we use old municipal solid waste or incinerated municipal solid waste for geotechnical reuse? And we are talking of earth dams, road and rail embankments, filling of low-lying areas, embankments of canals and lakes, backfill materials behind retaining structures. So we have all done properties of ash and properties of mine tailings. Do you recall them? We did these two materials. These are slurry deposited materials, right? Was there anything which was bothersome for you when we did ash? We talked about pond ash, we talked about fly ash, we talked about bottom ash, and basically it was all silica matrix. They had no biodegradable components. There were some issues of the environmental concerns, mostly relating to erosion, erodibility, but some thoughts about heavy metals and other issues. However, if your ash does not have leachable heavy metals, it's basically a material which is in the silt and sand size range. You can definitely use it for the purpose of earthworks. However, it should not remain exposed. So any design is designed like a normal soil. You will determine the properties of pond ash, find C dash, phi dash, CC, permeability, do the stability analysis and make the embankment. So here it's just showing a road embankment. There is no drain in it because it's not designed like a water retaining structure. So the entire soil can be replaced by compacted pond ash. An important design aspect is to cover the ash in an envelope of soil and vegetation to prevent any dust or rainwater erosion. So if you have pond ash available nearby, say easy to transport distance, local soil will be much more expensive than ash. Ash will be available to you free. Why? Because the thermal power plant will want to create capacity in its pond to put more ash. So they will offer it to you free. You may even sometimes negotiate, can you do half the transportation cost? Or can you deliver it to me? And that's for the thermal power station to see. If the thermal power station's ponds are full, what will they do? They'll say, okay, we will, how far is your site? You'll say, I'm 12 kilometers. Okay, we will deliver it to your site, because they want the capacity very urgently. However, if they have capacity for the next 20 years, they may not want to give you ash transportation cost free, but they'll say, okay, send your trucks, you can take it. So I can use it, but I am showing an alternate design here also. See, while the embankment is being constructed, it is constructed in layers, and I cannot construct from bottom to top in one day, right? So what happens when you have layers, you will finish construction, let us say here, for the end of the shift or 2 shifts or whatever. Then you will come in the next day. Now in the dry months, this will start to fly over the night, or it's dry. And if you are close to populated area, people are going to object. So a good design is to put intermediate soil covers, right? Even if the soil flies, it's not fly ash. So the local population is used to the local soil flying around. They are not used to a grey, fine ash flying around. So intermediate covers are a good idea, but they are rarely used because getting local soil is more expensive. Once you get used to the fact that your borrow area material is free, then you tell somebody, no, now in your design, please put local soil. And if you are a private contractor, you say this costs me much more, so I'd like to minimize this to the extent possible. People will tell you I can use sprinkling to do environmental control of ash, but believe me, I have not seen a sprinkling system in my past 20 years of working in geoenvironmental engineering, looking which is a sprinkler system which works all the time and doesn't allow ash to fly, and I have not seen one. The sprinkling system is put on whenever the visitor comes to the site, or maybe an hour before he comes, an hour after he goes away. And it is also used if it's very dusty for some peak critical times when you are working on it. But it is not used 24/7. It's not a luxury cost which is built into projects. Not only can we build road embankments, we can also build small dams and water retaining and embankments for retaining tailings and coal ash. So we have extensively designed in this country, if I am not off, maybe 50 of such structures which have risen either by the upstream incremental method or the downstream incremental to 50 meters and above, and they have performed very well. So you can use again in the middle of the embankment either compacted tailings or coal ash, but very important are these drains. If you don't make proper drains, it is not going to work, and most important is if you don't make the transition filters between the drain and the ash or the mine tailings. So transition filter design as per the filter criteria is extremely important. Having a rock toe is extremely important, and having a soil cover to encase and vegetation on it. Putting a soil cover by itself is not sufficient because eventually even the soil cover erodes. So if you have used a thin soil cover and you have a few rain cuts or rainwater gullies which are formed, then the ash gets exposed again. So the important thing is to have vegetation on it. And maintaining vegetation in arid climates is difficult. Maintaining vegetation in humid climates is fine. So you have to get local vegetation. So then the thickness of the cover is an item of debate. One would like the cover to be as thin as possible. How thin should be your cover? Let me say I am putting a cover at the top of ash. What is the thinnest cover that I can lay? I am putting a cover of local soil. How thin? Some idea? How thin can I lay? 1 millimeter? No. What about 10 millimeters? 10 millimeters, 1 centimeter. How are you going to lay 1 centimeter? Who's going to measure it? Who's going to make the payment? Because first you have to play, after all you're going to get earth, you're going to multiply it with that thickness and pay the contractor. Contractor will say, sir, I've laid it, but you have an undulating surface which may or may not be so precisely paved. So typically minimum thicknesses are in the order of tens of centimeters. Typically 6 inch thick is the minimum thickness which you can lay with the earth moving equipment. And 8 to 9 inches are the norm. And 1 foot is good, very good. And from the point of view of root zone penetration also 1 foot is a good thumb rule. But if you want to put shrubs whose roots are going to be deeper, then you'll have to put thicker covers. So this play-off between the thickness of the cover as an erosion control measure versus the additional cost of the local soil is something you have a trade-off. I am showing here a very interesting example which we did for Hindustan Zinc Limited. They were taking out ore, but before they reached the tailings they had to dig up the soil and the rock and then reach the tailing ore. In doing so they were producing something called rock muck. Now rock muck was nothing but rock fill, blasted material or drilled and blasted material. It would have a range from cobble sized down to sand sized, and instead of having a drain, instead of having a soil cover, because once you have, this was in Rajasthan site, Rajasthan is dry, most of the time maintaining vegetation is a big challenge. So we said, okay, we will design this like an earth cum rock fill dam. So this is a clay core type of situation, compacted tailings. There would be transition filters in between, and then this would be rock mix. This was available to us free because we could take it from the deposited material. This was available to us free because they were just stockpiling it after excavating it. So this design has been wonderful and it has worked very well. So small to medium height dams or dams of ash can be constructed with carefully designed drains, transition filters, rock toes and covers. For our IOCL project, they had several hundred acres of land, but the land had to be raised by 3 meters. So just take several hundred acres of land, multiply it by 3 meters and see how much earthwork is involved. And just multiply the earthwork by a cost like 500 rupees per cubic meter and you'll see how many crores of rupees are involved in raising the height of that plot. So they came to us, there was an ash pond nearby, and we did extensive testing before we allowed this to be adopted, and we looked at heavy metals, we looked at every possible contaminant which would come, and we've used ash for raising low-lying areas. There are no issues of settlement, the engineering behavior is fine, permeabilities are fine. The only issue is erodibility. When you dig it up to put a telephone cable or you dig it up to put a electricity cable, if you dig into ash, you have to be very, very careful. And even more, if you have utilities, water pipelines and sewage pipelines passing through this, you have to be careful. But otherwise, this material is fine. Why do you have to be careful? If a water pipeline leaks, even in soil, some soil will come in through the cracks. But if it's in ash, more will come because erodibility of ash is high, right? And similarly, in the flyovers now, at a lot of places, coal ash is being used as a backfill material for the purpose of for the purpose of retaining structures. Of course, a big change is occurring, which is slightly tricky. Earlier, all pond ashes used to be a mixture of bottom ash and fly ash. Now what's happening? Bottom ash is being consumed by the industry as a replacement for sand. So more and more pond ash is becoming fly ash. When it becomes fly ash, it actually does not meet the requirements of backfill for reinforced earth walls. If you look at the European standards and other standards, it does not meet those requirements. It's becoming finer than that. Indian Roads Congress has allowed use of pond ash without realizing the subtle change which is occurring. So one of our PhD students is working on this, that if the bottom ash is removed from pond ash over a period of time, how is it going to affect the behavior of reinforced earth walls? Because mostly backfill for reinforced earth has to be granular, it has to have a significantly high phi dash, and it has to be free draining. So as the coarse component goes out, it behaves more and more like silt, and that's a gray area about how it functions in terms of the pull-out capacities of the reinforcing elements which are put in the ash. However, this has been used in several places. Already I have told you about these issues. When you are going to consider waste reuse, you are going to look at the sources and quantities being generated in a city. You are going to look at what are the problems for disposal. As the capacities become full, the desire of the waste generator to give it out becomes more. As long as they have capacity, the person says, okay, the next person will take care of it when the capacity is full. We look at what are the potential reuses in geotechnical activities. We have to go through intensive physical and chemical testing. We have to look at the engineering properties. We have to address the environmental concerns of putting that material on soil. We have to look at economic considerations. Typically up to 50 kilometers away, now you can bring in all these waste materials if they are being given to you free of cost, and the material will be cheaper than the local soil, and then you have to see which applications they are useful for. So let us say, let's look at coal ash. The advantage of coal ash, it has relative low unit weight, it has high shear strength like granular material, which results in good bearing capacity as well as other minimal support or minimum settlements and other performance, reasonable slope stability, good behavior of reinforced earth walls in such materials. And bottom ash can be used to replace sand for drainage purposes. With all these interventions of the courts on mining from riverbeds and crushing of rock, availability of sand for drainage purposes is very, very low. So, a lot of pressure to use bottom ash to replace sands. Drawbacks I have already said, one is the proneness to erosion, so requires the erosion control measures, and sometimes ash will contain sulfates. If your coal has sulfur, which is not unusual, then the sulfur gets converted to SO3, SO4, so you will have sulfates. Now, you know that if you put concrete elements in soil with high sulfates, the sulfates attack the concrete, and the CSH gel and the products of reaction disrupt the cementation. So, if the sulfate content is high, then you have to take protection measures such as using waterproofing membranes or sulfate resistant cement. Those are required for the purpose of for design purposes. Critical to ash and mine tailings performing well over the long term is properly designed transition filters. None of the material the fines should not get washed out to start piping. And another important point is that if you are burying pipelines in ash or tailings, you may like to put soil blankets around them, that even if there is a little bit of crack or a fracture, then the material coming into the pipeline is soil, and you do not want ash to run into the pipelines. Let us also look at something which is happening as far as tires are concerned. Tires, as we know, we can retread them, we can reuse them, and we can reuse them. Eventually you can't reuse them. So what happens is, in America, these tires started coming to the landfills, and if a tire catches fire, then it starts to give out this thick fumes and all kind of gases which are injurious to health. So one of the ways to tackle this problem was to break up these tires into small particles, right? And these particles typically 1 centimeter cubes. You have some shredders and tire chip making devices, very economical. So all the tires can be converted to small chips in the gravel size range. So now you have a rubbery gravel, a gravel which is spongy. Why? Because the rubber itself is not a solid stiff matrix like silica particles, but it is a spongy, or it's got some movement which takes place. Doesn't matter where it is, doesn't have a load bearing role, there you can use this material. When radial tires started to come along, or reinforced tires started to come along, then there were wires in the tires. So the process of making chips became a little more expensive, because first you have to remove the wires. So none of the chips come with wires. So wires have to be taken out during the shredding operation, and you get these chips which are typically 1 to 2 centimeters in size. So they can be used in replacement of coarse sand gravel for internal drains. Definitely they can be used. They have more settlements, but the thickness of the drains is sufficient for them to continue to perform all right. In cold countries, one of the problems is that when you have snow, then the tendency is for the freezing to be above the ground also and below the ground. When there is freezing below the ground, what happens? If there is water, it will turn into ice, and as a consequence it will expand. If water will expand during cold months, the building will heave. So you want a protection called the frost penetration protection, and that can be done by putting a layer of tire chips, because they have low thermal conductivity and they reduce the frost penetration. That means frost will start from the top and start to solidify downwards, right? Your footing, let us say, is at 1 meter depth. If you have done a good design, you will find the frost penetration depth and keep your footing below it. So maybe your frost penetration depth is 1.5 meters and you have kept your footing at 1.75 meters. Now if instead of the soil I can put a layer of tire chips, the frost penetration depth gets reduced, because this is a thermally better material in terms of preventing frost penetration. So they are used in the developed countries for reducing frost penetration. They are also used in gas collection layers in landfills, and they are also used in drainage layers of covers Just beneath the topsoil you can use these for the purpose of. You can't use them in the leachate collection layer because the rubber may react with one or two of the constituents of the leachate, which may cause a problem. Let's look at blast furnace slag. Can I use slag for the purpose of earthworks? So it has been used as an aggregate in base and surface courses in asphalt pavements. The slag has also been used as an additive to Portland cement in concrete, and slag has also been used in embankments. So let's try and unravel what is slag. And this is the data which I picked up. So if you do chemical composition, we'd like to know what slag is. Is it silica? Is it what? So you see, it's basically silica and calcium, but calcium is in large quantities. Why is that so? It may be an additive. You know, in these processes, during your processing of the ore, lime may be an additive for some purpose. So here you are getting calcium oxide, silicon dioxide, that's the main matrix, plus other materials. So you have iron slag, you have steel slag, and if you look at the engineering properties, 2 to 2.5, 3.2 to 3.6 specific gravity, unit weight is in pounds per foot, let's forget about it, but absorption is there, abrasion values, sulfate soundness test, angle of internal friction, just look at the angle of internal friction. What we call angle of shearing resistance, pretty high, Mohs scale of hardness, caliper bearing ratio. So it has been used in embankments in the developed countries as a replacement for soil. It's a good material. What you don't get from both these tables is what is the grain size distribution. When you look at something as a soil, I can't sort of adjust to it until I see the grain size distribution. Just remember, it's a mixture of the various grain sizes, sand, silt, gravel grain sizes. And the advantages it is found is it can be placed in any weather. That means it's not like clay where you can't put it in, which becomes slushy like. In wet weather you can't put clay, but if you're compacting sand in wet weather, no problem. Rain comes, go and work, after 15 minutes the water would have gone away, your equipment can move. If you have clay, rain comes, please wait for a day till the site dries up before your equipment can go. So you can work in any weather. It has got extremely high stability and almost complete absence of settlement after compaction. And as I said, its high insulating value can be used as a protection against frost heaving. But there is a drawback. Because it has got calcium oxide. What is calcium oxide? Quicklime. Quicklime is reactive. And what will it become? Either it will become calcium hydroxide, CaO plus H2 will become COH2, or CO will react with carbon dioxide to become CaO plus CO2 equal to CaCO3. Now when you have a material which is going to absorb something from the atmosphere or react with it, then it is creating a new compound. Now as long as the new compound doesn't cause any volumetric changes, then it's fine. But if it's going to have a new texture, new volumetric changes, then it can be an issue. So because it has volumetric instability, you know, it gets some powdery precipitates which are formed because of the chemical reaction of carbon dioxide and the free lime. So that is a problem. It can result in clogging of drains and other outlets. So it is not a material which will not undergo volume stability. Material may not biodegrade with time. It is not something which will vanish, or it is not something which will reduce its volume, but because it reacts with carbon dioxide, its volume may. So if you have a flexible thing like an embankment, it is fine. But if you want to be in a place where flexibility is not acceptable, then slag cannot be used. So finally, I'd like to say that if you are doing geotechnical reuse, we are going to look at all the relevant engineering. For each waste, please remember that just because person A used slag at one location, that person B getting slag from another plant will use it is not possible. Similarly, if person X used coal ash from a particular thermal power station which may have no sulfates, person Y cannot use it from another thermal power station which may have sulfates. So, for every waste material you need to have the complete analysis about its chemical, physical characteristics, which is not what you do with soil. I will not pick up soil and start doing all kinds of chemical and leaching tests and TCLP tests. It is a natural material, it is formed over millions of years. We know that it has no harmful impact on the environment because people are living on it. But for wastes, at every location, all engineering, environmental, occupational health and safety, recyclability and economical issues are to be understood. You have to have a very high laboratory testing and assessment procedures for all the points that I gave you in the beginning, and you have to be able to have a criteria for approval or disapproval using the procedures. And if you are going to do the TCLP test, you know all the values beyond which you can't use it and below which you can use it. So, you need to have your criteria fixed, and sometimes with the waste material you may not have a criteria. You may have to set up your own criteria. And if sometimes the material does not meet all the standards, you can also consider pre-treatment. Now, what is the pre-treatment? I am not going to go into details because pre-treatments are expensive. The moment you do pre-treatment, you might find the local soil becomes much cheaper, or a soil from 30 kilometers bore area becomes much cheaper than the material that is being offered to you. However, in terms of economic considerations, you have to compare the full economics about the land area which is being occupied by the waste at the moment and how much area will become free. So, if it is necessary, you may reject the material, but possibility of pre-treatment to modify the material should always be considered. I mean, if it has got a little bit extra organic matter, can we do something? Can we do soil washing? Can we do heating to remove the organics? And if so, what is the cost, and can we get rid of the material from where it is occupying hundreds of acres of land? Also, we should be very clear that before we start the process, that if there are going to be any constraints on account of this material, if the material has bad smell, that is a constraint. I mean, you have bad smell, you start taking the material from an industrial area and start laying a road in a village, the villagers will be up in arms, and the NGO, the gases may be harmless, but purely because of the fact that it is producing bad smell, it may be a constraint in implementability. And also, nice if you are dealing with something new to have a demonstration project. Theoretically, everything may seem fine, but if you are making an embankment of a new material, defer it, do a 6 months demonstration project, make the embankment, make it go through the summer and the monsoons, and then if it looks fine, adopt it on a full scale basis. So, with this spectrum, you can cautiously adopt a lot of materials for geotechnical reuse, but some of the materials just get knocked off right in the very beginning. As I said, significant organics, significant salts, significant heavy metals, you are out. You have heavy metals, you might consider making blocks out of that, right? Why? Because you will be then fixing the material in a cement matrix and you can't release the heavy metals. As long as the brick building is in place, heavy metals are entrenched in that brick which you made from that material. So, in the building industry you can, but in geotech the material is going to be always in its original form. So, slowly those things can come out. So, some things will immediately say that this cannot be made use of. Other things, please be always ready for those special design measures, erosion control measures, should not enter into pipelines. It is very simple for us to say, oh, the CN5 is very good, CC is very low, permeability is good, it is a free draining coarse grained material. Does not matter, it still may be blowing dust in the air. So, we have to take those peculiar measures, specific design measures, such that it does not cause any problem to the local people, both during construction and after installation. Any questions or any thoughts which bother you? Okay, then we will stop here today, and in the next lecture we will take up can we use old waste. or can we use incinerated waste in geotechnical applications? Have a good day.